Metamaterials are used for shaping the flow of traveling waves. They are formed from periodic structures and can be engineered to have specific properties at different frequencies. This example is an optical mirror constructed from alternating dielectric materials with high reflectivity in this range. It's even used in Face ID. Band structures are a design tool for metamaterials. These describe which frequencies support propagating waves and which frequencies are strongly forbidden, like in this red region, called a band gap. For quantum devices, it's desirable to have simultaneous band gaps for light and sound. The standard method is iteratively generating band structures via finite element solvers and then checking if they satisfy constraints. Therefore, we seek a fast surrogate model that simultaneously predicts the optical and mechanical band structures to accelerate design.
Both the photonic and phononic problems are governed by similar physics. On the optics side, Maxwell's equations reduce a scalar eigenproblem for the electric field. The key material quantity here is the dielectric permittivity, and we generally expand in plane waves, assemble a matrix, invert, and solve for eigenvalues. On the mechanics side, we get a generalized eigenproblem involving density and the Lamé parameters. We generate all of our training data using Python solvers. We train on several geometry classes, all of which are on a square lattice. Here's an example for a circle. The mechanical bands are on the left, optical on the right, and we shade the band gap. For optics, we use plane wave expansion, and for mechanics, we use a triangle mesh finite element solver. We assume that our setting is silicon on air and that it is sufficient to calculate the true band gap to have 30 nodes per edge in our mesh solution, or 121 plane waves in our optics solution, and we verify that directly. We also assume that we only solve for TE polarization for optics and in-plane displacement for mechanics.
Our model architecture is rather complex, so we'll describe a simplified version of it. It's a physics-informed CAN meant to learn the Fourier domain physics that underlies band structures. Our CNN mirrors the Fourier decomposition step of numerical solvers, and they're following that there are two solver channels, one for each physics type. It has several layers, which use the smooth inverse activation function to approximate the matrix inversion of meshed material properties, which are normally used in numerical solutions for bands. The Silu activation function is smooth and differentiable everywhere and non-monotonic, so this is appropriate for modeling band structures. As for the sigmoid activation function, we use this to gate the mixing between the optics and mechanics, because the same geometry can have perturbations that affect both physics simultaneously. This model minimizes the mean square error for the normalized frequency over each band.
Here are the results. Red curves are CNN predictions, black ones are numerically solved ground truth. The prediction checks ground truth with high fidelity and low error around 2% over tests. Each of the prediction takes milliseconds. Because current architecture doesn't enforce band ordering, small errors near crossing points like in mechanical waves can result in massive divergence. Limitations. The model is limited to solve over 2D square geometries with presumed lossless two-material system. It cannot be generalized to hexagon, and the model computation misses out of plane wave behaviors, and pixelation may blur details. Thank you.